Kloosterman sums. So I write x bar for the inverse of x mod c and e of z for e to the 2 pi of z, as usual. And the Kloosterman sum with parameter m and c is the sum of over x that are invertible of e of mx plus nx bar over c. And we have the famous Weil bound saying that it's essentially of size c to the 1/2 plus epsilon, meaning we have a root cancellation for this sum. And if we want to generalize this, there's like an obvious generalization to GLN that was studied by Erdely and Todd and others, where you consider X a matrix this time in GLN Z mod CZ, and then you can compute E of trace of MX plus NX bar over C. And this Kloosterman sum appears in the application. So the first application is in the spirit of what Minley was speaking earlier. There is a geometric interpretation, but at the intersection of two orocycles. But in the end, I just think that if y bigger than 0 is integral, you look at the point x over y and x bar over y, where x and x bar are running, x is running over running mod y, and in the torus square, and this set using the Weil bound, you can quickly show that it distributes effectively in R of z square as y goes to infinity. And if you have bounds, non-trivial bounds on this GLN Kloosterman sums, then you can generalize this result to the same question over GLN, and this was done by Elbaz, Lee, and Strömbergsen, even in more generality. And another application of Kloosterman sums that I'm interested in, but I will not say more details for my sums about this, is the Peterson bound. So using Kloosterman sum, you can give this bound over Fourier coefficients of holomorphic modular forms, which is, in this case, we have, of course, Ramanujan bound, so it's less good, but in more general cases, it can be interesting to have something similar. And this comes from Peterson formula. So I want to speak about the symplectic Kloosterman sum. So the symplectic group is given using this J matrix, and we consider the matrices that are 2n by 2n that leave it invariant under congruent. And if we write M as a with n by n blocks, then this is it's actually equivalent to asking that the line, when you multiply with this transpose, are symmetric, and you have this kind of determinant congruence like D, A, C, B. When you make the difference, it's the identity. And in particular, if you take M with integral coefficients, then you have dA transpose is equal to the identity mod C times some matrix. So we could kind of say that D and A transpose are inverse of each other when you have a symplectic matrix with integral coefficients. And so from this, you can construct a more general Kloosterman sum. So this is the definition. So now I rewrite E of M for E to the 2 pi trace of M. And so if M is a number, it's the same thing. And this curly xn, I've read the symmetric matrices of size n for this. And I take two coefficients Q and T that are symmetric matrices, and take C with determinant on 0 and integral C. And I look at E of C to the minus T ATQ plus C to the minus 1 DT, where A and D are symplectic matrices, also that ABCD is a symplectic matrix with bottom left block C, and it's running over this double quotient by this unipotent subgroup, where you look at all matrices with the bottom left corner being C. And actually, if you fix C and you consider 1D mod C matrix, then there is a unique A in the quotient, and so you can just look at C kind of D mod C, and then A is the somehow inverse that we have to construct. And to do that, we have two lemmas that simplify. So I will just go quickly over it. So first, you can suppose that C is in Smith normal form, and furthermore, you can factorize the prime powers. So you can actually suppose that C is diagonal as just prime powers on the diagonal, and that they are increasing prime powers. And this was done by essentially Kitaoka for n equal 2, but the generalization is direct. Okay, and so if we have C like this, then D look like this. It's not symmetric, but it has like extra prime power here that gives this equation, which is the symmetry condition we have. And so if D is inverted, like if P, we know that the determinant of D is not divisible by P, and so we can construct an inverse of D as looking at the adjugate matrix and dividing by the determinant mod P. And then we have actually that D bar time D is equal to the identity mod C. And so we have this inverse matrix which corresponds to A transpose. And so we can rewrite our sum as this, replacing A transpose by D bar, and C is symmetric, so C transpose doesn't matter anymore. And we'll just running over D mod C with determinant not divisible by D, and so having this shape. And now you can, from this, read the trivial bound. The first line will run mod sigma 1, the second line mod sigma 2, and so on, and the last line mod sigma n. And we only look at things above the diagonal. So the trivial bound is given by P times the n times P to the n times sigma 1 times P to the n minus times sigma 2, and so on up to sigma n. So this is the trivial bound for a general C with prime for the diagonal. And so we have the following results that are work in progress. So Alfréd thought is looking at C being a scalar matrix, more like here I stated it for prime times the identity. And generically, it gets P over n squared over 2, and if you take the trivial bound over there, it will be n squared plus n over 2, so there's a win of n over 2. And me, I'm looking when you have different prime powers, and in that case, I get also a win of 1/2 here, which correspond, so which is like the corresponding bound generically. So meaning you have to ask that Q and T have determinant not divisible by P and maybe a bit more. And to finish, let me speak about the application in that case. You can consider now the orosphere and looking at the intersection sets again. And what you get is that you get two matrices, Z0 and Z infinity, that when you multiply by Y, which is an integral matrix, you have like some inverse matrices, like in the symplectic matrices. And in the symmetric case, it's really just the inverse matrix. From this bound on Kloosterman sums, you can show that this point Z0, Z infinity in the symmetric matrices mod 1 equidistribute effectively in this as Y get large, and this Y get large, I still have to work out how I do that because it depends on the bound on the Kloosterman sum, also probably at the non-trivial place. And so if you take Y equal m times 1, 0, and m goes to infinity, it's definitely correct, but probably a bit more. But you cannot just ask that the determinant goes to infinity, for example. Okay, I will stop here. Thank you.